and welcome to the Optimisation of Assets session at the Energy Networks Innovation Conference 2020. I'm Lucy Mason, I'm the Innovation Manager at Wales and West Utilities, and I will be your host for this session. The idea behind this Fast Followers session is for network operators to share with you some of the most beneficial technologies they have brought into business as usual after having explored them through either an NIC or an NIA project. They will be talking to you about how these technologies work, the benefits they've seen from their implementation into the business, and how other networks can apply the same solutions. From the audience, you can be a part of this too, by commenting or typing your questions into the chat bar to the right of your screen. Our speakers are logged in and ready to pitch in wherever they can offer advice. To get the best experience, we recommend that you close all other applications on your computer and check that no one else is using up your broadband connection. Now, let's get into those presentations.
Good afternoon. My name is Karina Jones and I am the Innovation Manager at National Grid Gas Transmission. Today I'm going to talk to you about the GRAID project undertaken through the RIIO-1 period. The Gas Robotic Agile Inspection Device, GRAID, has been developed in order to assess non-piggable pipelines in the RIIO-2 period. The GRAID robot is a first of its kind, able to inspect high-pressure gas pipelines up to 100 bar. The robot can climb 45-degree angles and has the ability to inspect the full 360 degrees of the internal pipe surface. This robotic device is tethered to allow the charging and data connection, but also allows for the robot to be towed back in the case of failure. The tether is 100 meters long and uses an umbilical management system to ensure the safety of the system. The original design of the robot utilized a magnetic flux leakage (MFL) sensor. However, these were proving too slow at an 11-week time period to inspect 10 meters of pipeline. In the past year, we have developed ART capability onto the robot with a company called Halfwave. This enables the completion of the same amount of work in only 1 week. The image shown provides a view of the GRAID robotic system, incorporating the ART sensor. You can see the ART sensors to the right of the robot, held by a robotic arm. And at present, the ART electronics is held in the tube seen to the back of the robot structure. The acoustic resonance technology will work in conjunction with the GRAID robotic platform, analysing the condition of critical assets by collecting essential data from inside the high-pressure gas pipelines. This includes wall thickness and defects. Acoustic resonance technology, ART, allows for improved signal integrity and signal conditioning, whilst decreasing the overall amounts of space required for the sensing equipment. The improved speed of the robotic sensing system allows us to reduce the time of inspection and therefore reducing the overall cost of the activity. Another key improvement of the ART sensor over the MFL sensor is its ability to assess coal tar enamel-coated pipelines, which is important for our RIIO-2 inspection requirements. The ART sensor works by sending out multiple frequencies of acoustic waves that produce oscillations in the pipeline wall. The resonance that occurs in the pipeline wall returns a sound signal to the sensor, and the frequencies returned allow the pipeline thickness and material characteristics to be determined through analytics software. The direct measurement provided by the GRAID robotic system allows very accurate measurement in comparison to the time of flight data that we see from pigging. The robotic arm that will manipulate the sensor is able to self-center and take measurements once directed to its measurement point. Movement of the robot through the pipelines is via magnetic tracks and is controlled externally by a driver above ground. The improved datasets that will be provided by the GRAID robot will eliminate unnecessary excavation and allow us to provide data that could extend the life of our assets. The reduction in excavation activity will also save us over 2,000 tonnes of carbon annually. Through the RIIO-2 period, we will be inspecting up to 20 compressor sites during planned outages and working closely with our asset risk teams to provide further insights into our AGI pipelines. The planned work has been included in the RIIO-2 business plan and is targeted to provide the network with around £30 million of savings through the reduction of excavation requirements. Work is looking to commence in 2021 and detailed planning of these activities is underway. If you would like further information around the GRAID robot, please contact us via our box.
Hi, my name is Mark Scarrett. I'm an Innovation Project Manager for SGN and Project Lead for the Pressure Control and Management Project, funded by the Network Innovation Allowance. In today's presentation, I'll be taking you through my latest overview and update of the project, starting with a section on demand response, then on to network monitoring, and finally automation. Demand response. In this section, I'll give you more of an insight into the project and how it's expected to benefit all GDNs. The two photos show the latest types of electronic actuator design developed by the project, a critical component of the new technology that's been evaluated. The electronic actuator system concept. Phase 1 commenced in 2017, seeing collaboration between SGN and a company called Autonomy, who came up with the original concept idea. The technical consultant SAFE also play a key role in the project team, providing additional technical support and appraisal. Autonomy's idea, that being to fit PRIs with remotely controlled electronic actuators that would enable effective automatic pressure control via software apps running from the cloud, captured SGN's interest, not least of which because the new technology looked simple to use and was also expected to demonstrate significant efficiencies over existing systems. The project duly kicked off and led to the realisation of a working prototype, which was in turn installed across 5 district governors for field trial in SGN's ROMSI network. Phase 1 produced some excellent data. However, several issues were encountered during the field trials. No showstoppers, but a reworking of the design became necessary. A Phase 2 workstream was then added to support further development, including a much wider range of field trialling assessment. And Wales and the West Utilities also expressed serious interest in Phase 2, consequently joining the project team as a collaborative GDN, adding their own expertise to the mix. And the graphic on this slide depicts the latest twin stream design with comms, with the 3 photos showing what the current physical installation looks like at one of the ROMSI sites. The main goal for this project is to develop a reliable and efficient pressure control and management system that will ultimately allow for the remote adjustment of PRI assets and offer UK GDNs the ability to react promptly to variances in demand without having to physically attend site to make pressure changes. Network monitoring. In this section, I'm going to expand on some of the strategy behind trialling this proposed technology. The image on this slide is a snapshot of the Data Explorer feature, accessed by an operative via their laptop or smartphone when using the system's digital dashboard. This dashboard is simply a digital visualization of the system operation, used to carry out a variety of tasks, including analyzing data, running data reports, and adjusting pressure settings. An integrated network. The images on this slide offer more detail on the ROMSI sites, along with an overview of how the operator communicates with the system via the cloud. ROMSI is a relatively small and localized integrated distribution network, lending itself well as an initial test bed to start evaluating the perceived optimization benefits. In Phase 1, only the working streams had actuators installed, leaving the standby streams as fail-safes. Each site was also fitted with its own logger to ensure good network visibility. Phase 2 used the same safe approach. However, enough confidence had been gained from Phase 1 to let actuators be fitted to the standby streams this time around, allowing for much more data to be captured. And like Phase 1, Phase 2 also starts with a basic clocking approach, ensuring the system can be programmed to a prescribed set point schedule before eventually ramping up to an operative attempting to manipulate pressure settings remotely. The latest field trial results have been encouraging, and the current intention is to expand the field trials over several other SGN sites to capture sufficient data to prove the ability of the new technology. Automation. In this section, I'm going to expand on the potential application for this proposed technology. The image on this slide shows another core system component, the controller, which has its own integrated battery pack and can also be programmed to run as a standalone clocking system without the need for comms or additional power source. Looking to the future. This final slide addresses what might be possible in the near future and the potential first steps toward a fully automated gas network. A range of future development possibilities are being considered, such as further digitalization enhancements, transmission applications, biomethane applications, hydrogen compatibility, artificial intelligence, and more. And the images on this slide include a couple of other possible network and GDN data dashboard reports. Also, the other images focusing on incorporating other network elements such as biomethane and transmission. The made-up pressure graphs imagining what the transition to a fully optimized AI network might actually look like. Network optimization by AI might sound a little far-fetched at present, but I believe our NIA project is the first building block for such a vision, and the next step may not now be too far away. And that's all from me. Thanks very much for listening. Bye.
Hello, I'm Richard Hines Cooper. I'm Head of Innovation at Northern Gas Networks. Leak Vision is a project all around developing technology systems to allow us to reduce disruption. When we look at leak sites, the current methodology is to use ground bar hauling to try and pinpoint readings that we can detect at the surface, link that back into the underground asset. That current method cannot determine how many leaks contribute towards the above ground readings, and what we can see from the photograph, which is Middlesbrough 1972, whenever we excavate, it creates a lot of disruption. Where there is a challenge, there's an opportunity. So gas readings that are taken from the surface, these readings actually often track from where the leakage location is. They follow the path of least resistance, which can actually be across through different substrata and actually come at a location completely different to where the actual leak point is. This can lead to missed excavations and several points of disruption that we need to pick back up, and it's a lot of time and expense that's incurred by the networks that creates disruption for customers. To further develop this scientific approach, this co-funded collaborative project between Northern Gas Networks and Synovate is allowing us to actually use in-pipe inspection to try and take that data to drive different levels of decision making. So really, do we repair the joint, or do we repair the multiple joints, or do we replace the pipe, and ultimately which is the best decision that's the most financially viable and the least disruptive for customers? We're looking to try and use this technology to help make better decisions. We're employing a traffic light system that allows us in, if you see a joint that comes back up and where you've got a red light that comes back up as an indicator, clearly that needs immediate action. If it's amber, this can be something that's deteriorated since the last time we've seen that, but it's not yet at a point where it warrants immediate action. Or if actually there's no particular point of interest and everything looks to be in particularly good condition, then we pick that up as a green, and that's something where we've got high confidence that that asset's in a good state of repair. Looking at the science, so this is actually all about leak vision. It's about thermal imaging and machine vision technology to allow us to actually look at the temperature within the pipe and the pipeline wall itself, and any change back in there that can help us pinpoint leakage. If you look at the image across on the right hand side there's a crack within that pipe, and you can see that there's different points of interest that are picked back up as a temperature variation. So, and actually this is actually within the pipe wall itself, and that's due to the fact that where we know that there's a leak. So there's a combination of thermal imaging, CCTV and gas sensors that can help us actually better understand the local environment within the asset, to then allow us to pinpoint that back in and take that back up to the reading that's up at the surface level, and again make better decisions around where we excavate and reduce the amount of disruption. So across the project we've used 3D computational fluid dynamic models. So we've worked with Synovate, who've developed this test rig. So this test rig allows us to simulate real world conditions and actually look to use the models that have been developed by TTP, the technology partnership, and actually understand the key relationships between actually the known leakage rate that we've simulated within this test rig and actually the change in temperature that the sensor can detect under precise conditions. So the thermal signature of the leak has been picked up, and at that point we're identifying actually we can undertake a quick comparison between the known environment within the pipe and actually what's happening at that particular joint itself against the known point of leakage. This then allows us to actually repeat that and infer the scale of leakage across a broader range of in-pipe assets. Deploying leak vision and reducing disruption on sites unlocks a significant range of benefits, going all the way from cost savings right through to environmental benefits and everything else that's associated. The progress to date on this project, we've now just approached the end of, we've just gone through stage 1. we've completed the first round of computational fluid dynamic modelling. So we now have an analytical framework for leakage and a proof of concept sensor package, which is just demonstrated across on the right hand side of the slide. So this is now actually showing a strong correlation between the simulations that were within the test rig and the expected results to actually say when we've got a leak at this particular point in time, what we're expecting to see within the model, and the two are just picking back up. So we're really encouraged by what we've seen so far across this project. Thank you. For any information, please contact me at the email address there, or any one of my colleagues at innovation@northerngas.co.uk. Thank you.
Good afternoon, and thank you for joining this Fast Followers session. My name is Vishal Danji, and I'm one of the Innovation Project Managers at Cadent. So today I'm going to be taking you through a quick presentation on the foam bag operation on stubs project. So this was an NIA-funded collaborative project between ourselves and Steve Vick that took place over the past year. So this project really came about to address the continued issue of stub ends or stranded mains on our network. These mains tend to be very costly or impractical to excavate directly above and have presented significant challenges across all our networks through our mains replacement works. Typically these mains are below busy road junctions or in areas where we would not want to limit traffic flow or access, such as outside hospitals. The sites shown on this slide are a perfect example of the challenges presented by stranded mains. The first, a site attended by Steve Vick, shows a typical excavation on a main, which then continues onto a busy road junction. The second picture, one from Project Field Trials, is a main road with a 4-road junction coming onto it. The stranded main travels into the main road, connecting onto a parent main along the middle of the road. So looking at our current options on site, there are two primary solutions. The first, to excavate in the entirety of the main, and the second, to use sealback 1.5. The traditional cutout method, however, has a large cost involved and tends to be the most disruptive to the public, with road closures and traffic management likely. The second option, sealback, provides the opportunity to remotely perform an insertion procedure. However, use on site has found it to be severely limited, with jobs often having to be abandoned due to insertion being impacted by bends or joints or rust or contaminants within the main. In addition to this, the insertion lengths possible are relatively short. So this presented us with a challenge to develop a technique to deal with these shortcomings. To address this challenge, Steve Vick went away and developed the FBOS, Nosecone and Insertion system. The Nosecone shown consists of a protective cap at the front. This is closely followed by a foam bag. Finally, at the back of the fitting, there is an electrofusion fitting to attach the Nosecone to the PE coil. The Nosecone is then inserted into the metallic main under live conditions, and this is through the use of the pictured gland box. The coil with the Nosecone attached, along with 2 umbilical cords, is then inserted for the full length of the main, up to the parent main. Throughout this procedure, a camera is in place to guide the insertion. Following this, a controlled volume of foam is then injected into the foam bag. This is then allowed to cure for half an hour. Once the foam bag at the front of the Nosecone has expanded and formed a primary seal, a secondary injection of foam is then performed through the secondary umbilical. This then fills the entire annular space between the PE and the original main. Once again, the foam fill is performed with a controlled volume of foam. This is to ensure that the entire annular space is completely filled. The foam is then left to cure, and the PE now can be pieced in as usual. So the FBOS system provides us with several benefits, with the operation currently covering both the 4-inch and 6-inch sizes, and the opportunity to undertake the operation on both 1- or 2-way fed mains. The benefits are wide-ranging, but the system allows for longer insertion lengths to be performed than previously possible, and an improved ability to deal with bends and joints, as well as rust or contaminants within the main when forming a seal. All in all, the operation can significantly reduce disruption to the public, and there are cost savings associated with the reduced excavation and traffic management requirements. So what's next with the project? We're currently in the final stages of policy sign-off following the trial period under G23. It will soon be available to all other GDNs directly from Steve Vick, with further info on trial data and documentation being available to share from Cadent. There's a large opportunity across the Tier 1 mains replacement portfolio, but we're also looking into the potential to scale up to both the 8-inch and 12-inch sizes. Thanks again for your time today. Both myself and representatives from Steve Vick will be available in the chat after the presentation session for any questions you may have.
The robotic roadwork and excavation system addresses three main problems for gas utility excavation work. Inherently risky operations that have the potential to have an impact financially, an impact to the environment, traffic disruption, and significant CO2 emissions created by large and heavy equipment, and the risk of damaging unknown third-party utility infrastructure. This can lead to loss of supplies, disruption to customers, and the potential for significant risk or injury to operatives.
The ENIC mechanism has given the gas and electricity industries the capability to drive industry change on a scale they just wouldn't have been able to before. And the winners out of that are our customers, because our customers see on the ground the benefits of the projects like RES.
The robotic roadworks and excavation system is an all-in-one solution with endless possibilities for future applications. We've put together a really diverse team here at ULC, and the results of our development have been amazing.
With the use of AI and robotics, we have developed a platform that can carry out complicated and critical tasks in this ever-changing environment of roadworks. This platform will conduct the end-to-end operations within hours, which used to take days or even weeks. This is a fully electric track-mounted robotic system that utilizes a high-precision robotic arm to conduct sensitive and precise work on the road. The variety of sensors on board of the robot creates a level of awareness for the machine to do its work in a safe manner. At the beginning of the operation, the robot uses a suite of non-destructive sensors to scan the ground and identify locations of the assets. The onboard software will then process the data and create a 3D model of these assets, which will guide the rest of the operation. After defining the best location for excavation, the robot cuts the road surface using a custom-made road cutting tool. Because of the flexibility of the robotic arm and the power of this tool, the system can cut and remove different shaped cores from the ground. Once a core is taken out of the road surface, we utilize supersonic air nozzles to agitate the soil above buried targets and remove them through vacuum excavation. Use of AI enables the robot to avoid any contact with the assets and prevents causing any damages to them as well. After exposing the target under the ground, the robot will use a series of custom tools and carry out a variety of operations on the pipe, like installation of a fitting. Once the operation is completed, the robot compacts recycled material in the excavated keyhole, replaces the core back in its place, and reinstates the road. The ultimate goal of the robotic roadworks and excavation system is to provide operators who are in the front lines of this risky work with better tools to carry out these tasks much more safely and more efficiently.
The benefits are cross-transferable to a number of utility, infrastructure and construction sectors. This will enable us to create new jobs for our operatives whilst upskilling them at the same time as we continue to invest in our people. We'll also help the industry at large in our transition to a net zero future.
So RES is really an all-in-one solution for excavation. And it's not just excavation for the gas industry, this can be excavation for any other utility, along with the capability for them to, in their own time, develop tooling that replaces their routine operations. I'm really looking forward to walking through London or the streets of any city in the UK or around the world at some point and seeing Res Systems working on this hugely diverse portfolio of infrastructure.
The Robotic Roadworks and Excavation System provides a new means of thinking about excavation. We want to thank our collaboration partners, SGN, and also Ofgem for creating a mechanism by which to fund future innovations in the utility space.
Thanks so much to our fast follower speakers and to all of you for coming along and participating in our Optimisation of Assets session. If you'd like to continue the discussion, you can head right over to the Innovation and Exhibition halls where you can access additional innovation project videos from the networks. You can chat live with project leaders and technical experts and check out the latest technologies on display on our interactive stands. That's all from me, and I look forward to seeing you again in this room at 3:30 when we'll be discussing consumer vulnerability.